This is a video for AQA Further Pure Mathematics. This is Sequences and Series 2.2, where we're looking at using induction to prove results about matrices. Usually when we're looking at this sort of question, it will be involving a matrix to the power n. So for example, we might be asked to prove by induction that the matrix 3, negative 4, 1, negative 1 to the power n is equal to the given result 2n plus 1, negative 4n, n, and negative 2n plus 1. Well, remember then that proof by induction has got these three steps. Step 1, the basic step, is where we look at proving that the result is true for the first value, and that's usually n equal to 1. The second step, what's called the inductive step, is that if it's true, or we assume it's true for n equal to k, then to show that that means that it's also true for n equal to k plus 1, the next value. And then finally the conclusion puts those two things together to make a statement about mathematical induction. Well, looking at the first step of that then, when n is equal to 1, we can see that the left hand side is just equal to 3, negative 4, 1, minus 1 to the power 1, which is clearly just itself 3, negative 4, 1, negative 1. The right hand side of the equation is equal to 2 multiplied by 1 plus 1, minus 4 multiplied by 1, 1, and minus 2 multiplied by 1 plus 1. And if we calculate that, we get 3, negative 4, 1, and negative 1. So clearly it's true for n equal to 1. Once we've done the basis step, we've then got to move on to the inductive step, which says that we assume that it's true for n equal to k. In other words, we have that 3, negative 4, 1, negative 1 to the power k is equal to 2k plus 1, negative 4k, k, and negative 2k plus 1. And then substituting n equal to k plus 1 into the right hand side, or into the equation itself, you can see that what we're required to show is that 3 minus 4, 1, negative 1 to the power k plus 1 is equal to 2k plus 3, negative 4k minus 4, k plus 1, and negative 2k minus 1. So that's putting n equal to k plus 1 into this equation here. We've got the matrix to the power k plus 1, so we can write that as being the matrix to the power k multiplied by then just the matrix 3, negative 4, 1, negative 1. So that's going to be the case for any matrix. We can say to the power k plus 1 is equal to the power k multiplied by power 1. So then, using just our usual way of multiplying matrices together, we can first of all write our result for the matrix to the power k, which we're assuming to be correct, which is 2k plus 1 minus 4k, k, and minus 2k plus 1. And we're going to multiply that by 3, negative 4, 1, and negative 1. So looking at the first row multiplied by the first column, we get there 3 multiplied by 2k plus 1, so that's 6k plus 3, and then minus 4k. The first row multiplied by the second column gives minus 8k minus 4, and then plus 4k. Then moving to the second row, and the first column get 3k, then minus 2k plus 1, and finally the second row multiplied by the second column gives us minus 4k and then plus 2k minus 1. So in total then we have 2k plus 3 minus 4k minus 4 k plus 1 and minus 2k minus 1, which is the result that we wanted. But just to emphasize that we've now got our result correct for k plus 1, we could write this as being 2 times k plus 1 minus 4 times k plus 1 k plus 1 and then minus 2k plus 1 plus 1. So there it is, written out nice and neatly. So we've proved that if the result is true for n equal to k, it is also true for n equal to k plus 1. Now put that together with the fact that we know that it's true for n equal to 1, we can then draw our conclusion to say that we've shown that if it's true for n equal to k, it's true for n equal to k plus 1, it's also true for n equal to 1, and therefore it's true for all values n greater than or equal to 1. Well, that's the end of this video on induction and matrices. In the next video we'll be looking at using induction to prove results about divisibility.